Hello friends, this video on DNF block elements part 32 is brought to you by examfear.com. No more fear from exam. Next we'll talk about the actinides. The actinides are these elements, they are 14 elements. Actinides from thorium to lawrencium. These are actinides, and please note all the actinides are radioactive. Okay, lanthanum, only this was radioactive, but actinides all are radioactive. Earlier members has relatively long T-half, but the later ones has very short T-half in second, 30 seconds, 60 seconds like that. And later ones actually can all be prepared at the macroscopic level. We'll see that. You can't even see that. You can't even see this element because they are produced only at the macroscopic level, in the nanograms level. And thus their study is difficult. The early ones actually you can prepare in the microscope, bigger levels. Okay, you can prepare in kgs, but the later ones actually can prepare only in the microscopic level. We'll see all these metals now. So let's say hi to all these metals. The first lanthanide is thorium, atomic number 90, and this is silvery white. You'll see most of these metals are silvery white, discovered in 1829, and this is named after Thor. Thor is what? God of thunder. Okay, this was used as light source in the gas mantle. You must have seen this gas stove, this light gas one, where we have this gas cylinder and we have this gas, right? Gas mantle. So earlier it was used for gas mantle, but since it is radioactive, so now it is not used. It is used in high-end optics. It is used as nuclear fuel, thorium, nuclear fuel. And it is also used for radiation shielding. Radiation shielding. And it is used for age dating also. This is thorium. The next is Proactinium. This is again silvery white gray metal. It also readily oxidizes when air. This is toxic, and this is radioactive. This is rare also. And actually Mendeleev predicted this. It was identified in 1930. So Mendeleev predicted this element, that there will be some element like this, and this name is from actually proto. Proto is means parent, and actinium is again element. So it's called parent of actinium. So it's called Proactinium. Okay, and this is used in the radioactive decay. This is the actually product in the radioactive decay. Sorry, actinium is the product of radioactive decay of proactinium. Proactinium, from this you get actinium. Okay, this is used generally for scientific research. You will see most of the elements, they are used generally for scientific research or nuclear fuel. The next is uranium. This is also silvery white metal, and it forms oxide coating. This is also radioactive. In fact, all these elements are radioactive. The actinide series, uranium-238, that is the most common uranium. It accounts for almost 93% of uranium in this nature, and this decays slowly by emitting alpha particles. This gives alpha particles, and this is used as nuclear fuel. Uranium is the most popular nuclear fuel. Okay, the next is Neptunium. Neptunium is again since it is just placed after uranium, and uranium, as you know, the word came from this planet Uranus. So this came from this. After Uranus we have Neptune. So with that it got this name Neptunium after this planet. This is also silvery white. It tarnishes when oxidized in air, exposed in air. Mendeleev predicted this element also, because that time it was not there. It was synthesized in 1940. It was first synthesized in 1940, and it was produced by bombarding uranium with neutrons in the nuclear reactors. And you'll see after this most of these elements are synthesized, and these can also be used to create nuclear weapons. It has 19 radioactive isotopes. The next is plutonium. Plutonium, again, after Uranus you have Pluto in the solar system. So this after after Neptune you have Pluto. So this is plutonium, named after this planet Pluto. Okay, this is also silver gray dull coating. It create the dull coating. It is radioactive, and this is also used for nuclear weapons. First synthesized in the same year 1940. Again, this also was synthesized by bombarding uranium-238 with deuterons. Okay, and this was actually used in the nuclear bomb in Nagasaki in August 1945. So this plutonium bomb, it was the plutonium bomb, plutonium-238. This was used as a nuclear bomb for Japan blast 1945. This is americium, named after America, because by this time America was developed. It was produced in 1944, and this was produced by bombarding uranium with neutrons in the nuclear reactor. Okay. The next is Curium. This was named after Marie Curie. Marie Curie must be knowing, a very popular scientist. And also Pierre Curie. So both were couple, husband wife. And it was produced in 1944 July by bombarding uranium and plutonium with neutrons in the nuclear reactor. Okay. In fact, 1 ton of the nuclear fuel could produce only 20 grams of curium. Such is the waste, right? 1 ton of nuclear fuel, that is uranium, 1 ton of nuclear fuel, that is uranium, produce only 20 gram of curium. The next is berkelium. This berkelium is, again, if you see, again silvery white. This is named after Berkeley. Berkeley is what? This is in California, and this is the place where it was discovered in 1949. Okay, and this is the 5th trans-Uranus element after Uranus, and it is also produced by bombarding Curium with high energy alpha particles. These are all synthetic elements, they don't exist in nature. Next is californium. It was produced in 1950, named after California, and it was also produced by bombarding Curium with alpha particles. It was produced in the University of California, so it was given the name californium. And actually this is used to start the nuclear reactor. Then we have einsteinium. This is also silvery white radioactive, and this is named after our scientist Einstein. This was identified in 1952, again by University of California. Fermium, this is the last element that can be prepared at the macroscopic level. So after this you will not see the figure. Fermium. And this was again named after Fermi, famous scientist, and discovered in the debris of first hydrogen bomb explosion in 1952. Right, so in that it was formed. Next is Meelium. So this was again synthesized by bombarding einsteinium with alpha particles. It was synthesized in 1955, University of California again. Right, it cannot be prepared at macroscopic level. You can't prepare 2 or 3 grams. It prepared only the nanograms at the macroscopic level. Sorry, microscopic level. The next is Nobelium. It was prepared in 1958. Again, it was synthesized actually by University of California, I think, yeah. And this was named after Alfred Nobel. And then we have, next element is lawrencium. This is lawrencium. This lawrencium actually was again prepared by Lawrence Berkeley Lab of University of California. So it was named after Ernst Lawrence, lawrencium. So if you see the electronic configuration of these elements, you will see that they all have 7s2, and they all have variable F. F can 5F can actually have 0 to 14 elements. 0 to 14 elements. Okay, and S will have 7S will have 2 elements, and D will also have 0 to 2 elements, so 1 element. Yeah, 1 is the maximum we can see here. Okay, so it is believed to have 7s2, and it has a variable occupancy of 5F and 60 subshell, but not much is known clearly because these elements are produced only at the microscopic level. You see the atomic size decrease here, similar to lanthanide contraction. We have actinide contraction here. Here also due to poor shielding effect. Lanthanides was poor shielding effect of 4f orbital. Here it is poor shielding effect of 5f orbital. Not much is known about the atomic size of the later ones, but whatever is known, there is a gradual decrease in the atomic size. Talk about the oxidation state. It has a great range of oxidation state. Why? Because my 5f, 60 and 7s, these 3 orbitals are involved, right? The last few, here we have all the electrons, valence shell, valence orbitals, and these orbitals have almost comparable energy, and thus you have variable oxidation state. For example, uranium has 4 oxidation state, right? This plutonium has 5 oxidation state. Okay, let's talk about the general characteristics. They are all silvery white, highly reactive. They are all radioactive. They are not attacked by alkali because of the formation of this protective coating, but they tarnish easily rapidly in air. But not much is investigated about these elements because one is they are radioactive and they don't have very big T-half. They easily disintegrate. The half-life is very less, but most of them are. Thank you. Visit examfear.com to watch more videos, attempt free online tests, get free study materials, find tutors and mentors, and much more. Thanks once again.